Okay, so we're going to solve this problem. We've got 100 positive integers. They're all less than 100, so they're all between 1 and 99, and they add up to 200. We need to prove that whatever these integers are, there's always going to be a way of splitting them up into two disjoint subsets, where the sum of the integers in each subset is 100. And the sort of approach we'll take is, we'll essentially imagine that we've got a partition where it's reasonably close to being 100 each, and we'll have a look at the sort of tweaks that we can make, so perhaps moving numbers around from one set to the other to try and reduce this difference. So we'll introduce some notation here. We'll say that we've got S and B are a partition of these numbers, and we're going to go for a proof by contradiction sort of approach. So we'll say that this is a partition which actually minimizes the difference. So it minimizes the difference between the two sums. So we'll call this difference D, and we'll say that S is going to be our sum with the smaller sum, and B is going to be our set with the bigger sum. So we'll say that the sum over S, just informally, is less than or equal to the sum of our numbers in B. So the important assumption for contradiction here is going to be, we'll assume that D is greater than 0. So the difference is greater than 0, which means that you can't split them up into two subsets with a sum of 100 each. So now if the difference is greater than 0, the closest you can get is 101 and 99. So actually the difference then has got to be greater than or equal to 2. So now let's have a look at the sort of things we can do to try and reduce this difference. So the simplest thing we could do is perhaps just take a number from B and move it to S to increase the value of the small sum and decrease the value of the big sum. So let's imagine we can move 1 from the big sum into the small sum. What happens here? Well, just with some numerical examples, let's say you had a partition with 105 as your big sum and 95 as your small sum. This would reduce our difference. You'd be down to 104 and 96. And if you had 101 and 99, then you could reduce this all the way so that they're even, so you get 100 and 100. Of course, this is a contradiction because we've assumed that this partition minimizes the difference. So the problem here is that I've assumed that 1 is in our set B. So we can assume then, if this assumption is true, then 1 is not contained in our set B. So we're already seeing some quite heavy restrictions here on the number 1. So let's explore this a bit further. So if there's no 1s in the set B, what if there are no 1s in the set S either? So there's not any 1s in our numbers at all. Well, we've got 100 positive integers. They add up to 200. And if there are no 1s whatsoever, then we've actually got to have all 2s, because let's imagine you start off, you've got 100 2s, this adds up to 200. As soon as you make anything bigger than a 2, it's too big and the sum is over 200. So actually, it's not possible to have no 1s at all, because then you've got just all 2s, and of course you can split this up, just have 50 2s is one set, and the other 50 2s are your other set. So we can actually say then that 1 has to be contained in S, because otherwise we can partition this, and this contradicts our assumption. If there's no 1s whatsoever, this contradicts our assumption that the minimum difference is greater than 0. And now the fact that there's a 1 in our smaller sum is actually really useful, because this rules out the possibility of there being a 2 in our bigger sum. So just to illustrate this, let's imagine we've got a 1 in S and we've got a 2 in B. Then you could swap this 1 and this 2 around, so the net change for S would be +1, the net change for B would be -1, and this would reduce our difference between them. But we've assumed that this difference is minimized, so this would be a contradiction to our assumption. So this actually rules out the possibility of there being a 2 in B. So we can say that if there's a 1 in S, this implies that we know that 1 can't be contained in B already, but now 1 and 2 can't be contained in B. We can probe further here, because let's imagine now there are 2 1s in S. Then this already rules out the possibility of 2 being in there, because you could swap that for one of the 1s. But it also rules out the possibility of having a 3, because you could swap these two 1s for this 3 to get a change of +1 here and -1, which would reduce our difference and be a contradiction. So now if you've got 2 1s in S, this implies that we've got 1, 2, and 3. None of these can be contained in B. So B would only contain numbers which are greater than or equal to 4. So we're getting some quite heavy restrictions here. And similarly, if we had K 1s in our set S, then this would rule out B containing anything up to K +1, because you could swap these k1s for this k plus 1, still get a change of +1 and -1, which would contradict our assumption of minimality. So we can say now, if you've got k1s in S, this implies that everything from 1 all the way up to k plus 1, these are ruled out from our set B now, and this is telling us then that B contains only integers which are greater than or equal to k plus 2 then. We'll just write this informally as the minimum of B is greater than or equal to k plus 2. So if we've got a lot of 1s in S, then B has to contain some quite large integers. But this actually works both ways, because if we contain a large integer, then in order for the sum of our 100 positive integers to still be 200, we're going to have to include a lot of 1s just to make sure that it's not too big. So you can think of this, we've got 100 integers, the sum is 200, so the mean is going to be 2. So if we contain a 3, this tells us then that there must be at least 1 1 in S to balance this out. There's no 1s in B, so it has to go in S. If we contained a 4, then you would need 2 1s in S to balance this out. And similarly, if we had an n, then you would need to have actually n minus 2 1s in S to balance this out. And these are all just lower bounds as well. This is just to balance this n, so we ought to say greater than or equal to this many 1s in S. And we can go further as well, because let's say we've got A and B, then we need to have A minus 2 1s to cancel out the A, but we also need to have B minus 2 1s to cancel out the B. So this is where we can get a contradiction now, because let's assume that B contains at least 2 elements, which is sensible, and we'll say that K, we'll just fix K as the number of 1s in S. So now we've got k 1s in S, so this tells us that the smallest number we can have in B is k plus 2, so the minimum of B is greater than or equal to k plus 2. And we've got at least 2 of these, so for each of these you've got k plus 2 minus 2 1s in S in order for the mean to still be 2. So this tells us that we've got at least 2 lots of k, so at least 2 k 1s in S. But this is a problem now, because k was supposed to be the number of 1s in S. So you've got k has now got to be greater than or equal to 2k. And we know that 1 is contained in S, so k does have to be greater than 0. And of course this is now impossible. So we get a contradiction here, assuming that B contains more than 1 element. So this tells us then that B has to only contain 1 element. So we've got our sum, which is supposed to be bigger than the other sum, only contains 1 element. But this is a problem as well, and this can't work because the biggest integer we're allowed to include is 99. They're all less than 100. So this is telling us then that our sum has to contain only 99 at most, but it's got to be greater than 100. So this is a contradiction once again. So B can't have more than 1 element, it can't have 1 element, it certainly can't have 0. So this contradicts our original assumption then, where we've minimized the difference between our two sums, and we assumed that the difference was greater than 0. So this tells us then that the difference is 0, which means that we can split our sum up into 2 smaller sums, each of which has sum equal to 100.